This presentation is titled Implementing Machine Learning Algorithms in Raku. My name is Anton Antonov and I'm a senior research scientist. I also brand myself as a senior data scientist. So this presentation is for the Raku conference 2022. Okay, so in this presentation we're going to discuss machine learning workflows, demonstration of those workflows for some interesting, in my opinion, Raku examples, Raku use cases. I would like to discuss the software engineering perspectives of doing machine learning implementations in Raku and in general. And ideally, it's going to be clear that there's some kind of unique ways to utilize machine learning into Raku's unique features. So the algorithms considered here, they're in this list, but actually the next slide is probably better. So here, this mind map shows the machine learning algorithms I'm currently working on, and I have marked the ones which I have implemented. So machine learning can be split into three categories: supervised learning, unsupervised learning, and reinforcement learning, which I have not included here. But for reinforcement learning, you need to have these two, the supervised and unsupervised ones. Some people have successfully convinced me that data wrangling should be included into the machine learning workflows, although that's not machine learning per se. Nevertheless, it's very important to have good data wrangling capabilities, quite a lot of data preprocessing and feature extraction, fundamental data analysis, just getting oriented what the data is. These are very important in order to do successful machine learning algorithms. All right, so here I would like to mention first that the presentation is somewhat inverted. I think the examples which I find most interesting, they're going to be given first. So the first example is going to be Zeph ecosystem modules or packages recommender, and the other one is domain-specific languages grammars classifier. My assumption about the audience is that most of the people in the audience are interested in software engineering. Not so many interested in machine learning as an activity, right? Like implementing machine learning algorithms. Almost everyone has been exposed to machine learning algorithms in one way or the other. And significant amount of people know at least some machine learning. All right, so here, yeah, this mind map just basically shows the plan, more detailed plan of the presentation. I am going to make the examples I mentioned first, and then I'm going to tell the big secret, about the software engineering observations, which spelled out here, and then we're going to do a machine learning algorithms walkthrough. Okay, so here in the first example, I'm going to demonstrate the Zeph ecosystems recommender. So I'm going to do it through the command line. So just a moment. So somewhere here, yeah. So somewhere here. So I'm using Shortcuts. Shortcuts is an application which is built into macOS or iOS, any kind of Apple operating system, any kind of Apple device contemporary enough comes with shortcuts, and I'm using a particular shortcut which extracts text from photos, right? And then I give it to this recommender, and then it's going to the recommender is going to produce some relevant results. So here's a screenshot from a blog post from someone from Raku's community. That's Steve Rowe. And I'm going to take the screenshot, right? And yeah, click on it. And then this extracted the text. It's not important is the text, do we copy it or not. With this option here from shortcuts is being written in this markdown file. And then this script in Python takes that file and produces recommendations, and we can see what say Dan pandas and etc. Right? They have something to do with what this text is. Right? So I'm going to do this in a slightly different way. I'm going to demonstrate this recommender. So I'm going to dictate to it math symbolics and data wrangling. Okay, that's absolutely terrible. I'm going to try to redo the whole thing. I apologize here, it's like Siri cannot parse my accent. Mathematical symbolic algorithms, data wrangling. Alright, so yeah, I mean, you can see whatever the results are, they have something to do with what was the text given here. Okay, so the other perspective we can have on this, and what I'm showing here is what I have done: speech recognition, text extraction from photos, and I'm going to do command parsing. This is using actually Raku. And so yeah, because you can tell me, well, this is a Python, it seems to be a Python script, and you're doing some macro stuff, but where is Raku in this? Well, you know, Raku is obviously in the actual recommender, what is being recommended, but let's actually show the actual Raku functionality is being plugged into this. So what is happening here is that I am doing this, invoking this script to search engine query code, which uses Google style advanced search specification and translates it into some command line interface type of specification, right? So this is with this CLI here. If I write here something like, say, you know, this is going to produce the sparse matrix recommender retrieval function, and if it is not clear, this is using the so-called Elasticsearch type of predicate specification. So if I do this here, this is going to translate this search, advanced search specification, Google style, is going to translate it into Elasticsearch specification with using should, must, and must not. Right? Okay, so this is done in Raku, right? Okay, and so, and what exactly is happening here? So I actually have used different machine learning algorithms to transfer some input from the user, and then I have some Python script which hydrates the whole some recommenders, say for Zeph ecosystem packages and modules. Then the actual recommendations are computed and some output is given, right? I mean, obviously, if I have staged my machine learning algorithms to work in this way, this means that I can do quite a lot of, say, I can deploy the whole thing on the cloud in one way or the other. I'm using Python because Python is very quick to hydrate machine learning artifacts or any kind of Python objects, but machine learning concretely, and basically I have this kind of serverless, you know, type of solution. It's very quick to use large recommenders, for example, in Python, in the way I was showing. Another interesting detail here is that I can do a mobile device version. Let me show the mobile devices. So this here, if I do, say, some kind of tag CLI, right, this is going to produce recommendations, you know, for, you know, with which adhere to this tag specification. Or if I do, say, tag Java, right, or something, I mean, I'll start have some, presumably I'll start have some maybe Java related type of recommendations. All right, so again, you know, what is going on, why I'm showing all these possibilities? Well, I do have this recommender system is implemented in 8 different languages, and my Raku implementation is a reference implementation for the Java stream blending recommender and the Swift stream blending recommender, also Kotlin. SQLite implementation, again, very similar to the Raku one. Mathematica and Python, they use sparse matrix algebra, and that's why they're called SMR, like sparse matrix recommender. The reason I'm mentioning this mind map here is that I actually, in this way, using command line interfaces and having quick to respond machine learning artifacts and scripts and so forth, right? I can deploy this in different platforms, on the cloud, but also mobile devices and so forth. All right, so this was the first example. The second example is about producing or making a domain-specific language classifiers. So I have this kind of commands. You can see here I can prompt the this function which is in Raku, what is exactly this specification trying to do. It belongs to the workflow called latent semantic analysis. But ideally I should be able to do this also without prompting it, right? This is what is happening here. So what you see here is basically it's a notebook. This presentation is a Mathematica notebook, and Mathematica lets me evaluate commands in different languages. This is actual shell implementation here. So I can just copy and paste this. Right, and kind of show it here in the command line, right? And so yeah, this is generating the R code, and what I'm saying is that I don't want this prompt to be happening, right? So I don't want to get this just a moment. So here I want to do this type of specification. And I mean, let's actually make it more interesting and say I'm going to say some other language here, say right? And this is going to produce R code, and it should be quick enough to figure out what exactly is being done. Okay, so what is the actual classifier? What is going on, right? And so in order to make this kind of classifier, I need to get the commands. I need to have some kind of textual data which tells me how to classify from text like this, how to classify into a corresponding workflow, say related semantic analysis. I have, say, a dozen of different grammars which are being understood by this function to DSL code, and I want to be quickly to figure out which one which one of the parsers, of the domain-specific language parsers I should apply. Of course, I can do a brute force type of algorithm, enumerate all of the parsers and see which was successful, and kind of fully parses the expressions, the textual specifications. But obviously we can speed up the work, and so if I don't have text commands, for this I need to accumulate them in some way. If I had millions of users using this system, I could have utilized that, but I don't. So either I write these commands manually or I generate them. So I actually did generate them with using grammars giving so-called production rules. So I generated random commands using grammars implemented in Mathematica. And here, since we're talking about recommenders, I'm going to show a Raku recommender for doing this type of classifications. So my data, you can see my data looks like this, like say show data outliers. This belongs to classification. This doesn't need to belong to classification though. Show data outliers can also be part of say recommendations. And some other commands here, like say generate a random data set with 383 rows. This belongs to the workflow random tabular data set. So I have this kind of data, like I have 5,000 commands like this, 5,220, which I have the actual sentences, the actual commands, and then labels, right, which tell me which workflow they belong to. It's like some sort of a summary. We very rarely have this kind of uniform distribution between the labels, but because this is generated data, I mean, I'm in control of that. So somewhere here I make the recommender. You can see after I have transformed the data, before I give it to the recommender, my recommender knows that each command has some kind of words, and they're associated with two different tag types, word and DSL. I'm trying from words, some kind of set of words to classify into this domain-specific language tags which are being given, right? And so here, after I have created the recommender, you can see that I'm saying classify by profile. I'm taking the words of this command, make the document term matrix, and I'm saying classify this to domain-specific language tag type. Since some of these words might not be known, I'm asked not be known by the recommender, I'm saying, well, ignore the unknown tags. And as a result, we get to this list of pairs, which the keys, they tell me the domain-specific languages, the workflows, and the values scores, right? These are not probabilities, these are scores. They're normalized to to the highest score which was obtained, and we can see for this command latent semantic analysis has the highest score, which kind of makes lots of sense. All right, so I can split my data into training and testing sets, create my recommender using the training data, and then evaluate it using the testing set. This is what is happening here. We want to see this kind of confusion matrix. These are the original tags and these are the predicted tags, and I want to see how often I'm recognizing the actual tag being assigned to the command, how often I recognize it with this recommender or this classifier. And maybe it's more informative to look into the actual frequencies, and so we can see that we have a fairly strong classifier, especially for random tabular data set. We have like 100% recognition over the test set we had, right? Quantile regression 75%, classification 86%, and I would consider this to be a fairly good classifier. I don't need 100% strong classifier, because you can see when I give it to this DSL translators, right? They just need to have some kind of order which is fairly adequate. So if, say, the first one doesn't actually parse the commands, I can, if the second one is the correct one, well, then I'm going to use that. All right, so yeah, basically this is it with the recommenders. Now in actuality, right, this thing which I'm showing in the command line here, it's actually using prefix trees. So here it's an example of this kind of prefix trees I'm using to do prefix trees with frequencies. This is what I'm using in order to make the classification. I'm going to expand more on that, right? Okay, so with the software engineering observations so far, from what we have seen, I have developed basically this style of implementation of machine learning algorithms. For me, which seems to be working, is to use functions as a front end of the functionalities, and to use object-oriented hierarchies for the different methods. And I'm going to explain this here. So I'm going to do this with, say, let's say clustering. Right. So this is this is a Python package, and we don't need this anymore. And here this was generated, plot was generated and put into into the other screen. So I have a function find clusters. I also have another function k-means. K-means is also a method of find clusters. And at this point I have implemented only one clustering algorithm. But say this clustering algorithm is using different distance functions from this role. If I have another clustering algorithms, like say k-medweights or bisectional k-means or whatever, right? They're going to be also using this kind of role. So this is what I mean by having functions as a front end and having object-oriented programming hierarchies for the different methods. Another example of this is to use association rule learning. So this is again putting it on my other screen, right? So it's more or less the same structure. So I have the functions frequent sets and association rules. I have the frequent sets finding functions a priori and a clut as standalone, but there are also methods for frequent sets. And you can see how a clut, for example, is based on some roles, and a priori also uses some of these roles. All right, so I mean, fairly kind of no-brainer, so to speak. In this presentation, as I mentioned, I'm using Mathematica notebooks, using notebook solutions and text tables and text plots is very important in order to get oriented into what machine learning algorithms using Raku or any other system are doing, right? So with Mathematica, I have strongly studied and observed the Jupyter solution to Raku, which is implemented by Brian Dugan. Some of the other presenters in the conference, I think Steve Rowe is most likely going to be using Jupyter notebooks. Fast data type deduction facilitation, I'm going to expand on that, but yes, of course, it would be very nice to know what kind of data we're dealing with. Model storage and deployment, I already commented on this. Raku is slow for this, from this perspective, but for the things I'm using, or for the things I need machine learning, which is mostly to facilitate generation of code through these domain-specific language translators, Raku it's fine enough. And to some extent, that's why I prefer prefix trees, because in my prefix tree implementation in Raku it's fairly fast to take models and use them as classifiers. Machine learning algorithms can be a bit really complicated with very complex and sometimes non-intuitive type of results. So unit testing, correctness testing, proper documentation, very important. Just the transparency of the algorithms as implementation, that's not enough. So proper documentation needs to be made with fully worked out examples. Command line interfaces as much as possible seems, again, this is one of the strong features of Raku, and yeah, basically it's both a brainstorming technique, I would say, for the machine learning algorithms implemented in Raku, but also something that makes them really useful, especially with this example with the pipelines I was showing earlier. A facilitation with code generation, I like this, obviously, and my presentation in the previous Raku conference in 2021 was heavily about this, right? Not many people actually are that interested in this, but well, I'm interested in it. So, okay, so this here, photos with using trucks, they kind of show my perspective of what I do data wrangling wise, not just with Raku, but in general. And so my perspective of having data wrangling functionalities in Raku, and before going further, let's actually show something here. So let's, I'm trying to invoke this mind map, right? Okay, so yeah, data wrangling, I need to do quite a lot of studies and also fundamental data analysis in order to do any kind of successful machine learning algorithm application. And so quickly figuring out where we're going, what we're doing, what is the data is very important. Some of the other people who are dealing with data in Raku have Raku modules. They have more like this kind of big robust perspective, and they're more interested in building pipelines with large data, which have some kind of repeatability and so forth, right? Yeah, again, I'm kind of more interested into getting working with samples of the data, figuring out what's going on. Of course, sometimes just dealing with samples is not enough. So if you have fast, reliable, robust algorithms, then yes, for data wrangling and studies, it's better. But my focus is more on the data study per se, right? Well, of course, also I'm interested in making machine learning frameworks. And another example here, most of the time, what I do, the algorithms I do, they're not for people off the street, so to speak. They're for data scientists or people who want to be data scientists, or part-time or full-time. And so the solutions, they need to be robust, but they're somewhat in kind of cleaner and simpler environment, especially when it comes to Raku. To some extent, that's why I don't want to do a lot of heavy machine learning studies and work with Raku, not currently, but I do want to facilitate heavy machine learning studies and implementations using Raku by generating code. Alright, so I mean, I probably already explained this to a point, but yeah, these are different approaches, I would say, to do data wrangling in Raku. Mine approach is very dataset based, and I explain what dataset is. It's minimalistic. This is with this package data reshapers. There's a comprehensive introduction to my approach here in WordPress. There's a data frame object-based approach by Steve Rowe. Again, he has fairly well documented his approach and intents. And of course, you know, the object relational mapping. This is red database, red package. Okay, when I was talking about minimalistic data wrangling implementation, I'm going to be somewhat more specific here. So I want the data to be easily transformed with typical built-in commands. So people who are not interested to know my approach to data wrangling, they can still use the outcomes of my data wrangling packages. So that's why I'm using datasets, not data frames. The datasets I'm talking about, they're just arrays of hashes or arrays of arrays. For me, this is a user experience or user interface type of design. So like previous presenter was talking about using map and how convenient that is. Yes, it's exactly that. The standard built-in functionalities in Raku should be very easily applied to whatever kind of data wrangling efforts I have, right? In whatever scripts and notebooks and so forth I'm doing. So I'm not sure why is this aborted. Let me see, is it going to work? I don't think for some reason this shell interface is not it's being blocked. I'm not going to fight it, but you can see here, for example, in this data wrangling code generation, I do have, say, a certain command, like say use df iris group by species show counts, right? And yeah, obviously I can do, this is here in the notebook, but here I can generate this code in the command line. I was thinking that using shortcuts, using some kind of other type of facilitation of code generation is going to be very convenient. Well, because I use these functionalities for my own work, to speed up my own work, using the command line interfaces for code generation was much more productive, right? Much more useful as a workflow. And so, yeah, this is what we're seeing here. Now, you can see that I also can use translate commands from Bulgarian. So this here, it's a similar command, but like this one in English, but in Bulgarian. And if you don't know Bulgarian for some reason, you can see the translation of this Bulgarian command into English. So I mentioned this in the previous year conference, Raku conference. Bulgarian is an analytical language. It's very similar to English grammar-wise, and Bulgarian in general is considered Slavic language mostly because of the vocabulary. But the grammar is similar to, say, English, as I said. And because of this, for some short commands like what you see here, it's relatively easy to transfer English grammars to make them Bulgarian grammars and to be able to parse Bulgarian commands. And there's some work to be done. It's not completely straightforward or trivial, but yeah, this is one of the things I mentioned in the previous year, and yes, I have done it here. I'm demonstrating it here. And one of the things I would like to kind of continue discussing in that regard is, yeah, you can see this is the big picture right now for data wrangling. This is not just for data wrangling. I have also other packages and systems, not just for data wrangling, but say for latent semantic analysis, for classification, for regression, and so forth, right? Now, I can interpret English or Bulgarian natural language commands into the concrete packages. Since we're talking about data wrangling and code generation, it's you can see here how I'm generating Raku code for the reshapers family of packages, and it's my to-do list to do this kind of Raku code generation for read and done packages. As I showed earlier, if I can do this for programming language, obviously I can do this for some of the natural languages. All right. So some data wrangling examples. So here, this is a Titanic data set, fairly well known. Kind of evaluated several times. So we have an ID which is kind of optional. We have the passenger sex, passenger survival, passenger age, and passenger class. This is the Titanic disaster, right? We have approximately 1,300 records, the people who have been there. Here's a sample of how this data set looks like. As I mentioned, my data sets, they're basically arrays or lists of hash objects. Here, if I transpose this, right, you can see this is actually a data frame type of perspective. So Dan, Steve, Ro, they live in this realm here. They basically use this column-oriented, column-based representation of the data. That's actually can be fairly convenient because then each of these columns you can have just say one type for that. Now Raku, and this is something I really like about Raku. Raku lets me have heterogeneous structures, right? Heterogeneous lists, heterogeneous hashes, and so forth, right? And so for me, again, you know, taking my minimalistic perspective, it just makes more sense to have a list of say hashes or list of lists or array of arrays. All right, so here we see some other examples of the code generation. I already went through that. So here about the grouping and counting, we can see how, you know, I have taken the Titanic dataset. I'm grouping by passenger sex and passenger class, and then we can see the actual groups. Fundamental operation is cross tabulation, maybe very useful for this kind of data, and we'll see some other elements. This data with prefix trees, we're going to see it, you know, being shown also, same data like what you see here, but this is cross tabulation. Cross tabulation tells me basically how often first and female appear together, right, or second and female, and so forth, right? And so some more complicated cross tabulation is to not just look at the frequency of appearances, but to also get to sum, to aggregate with this passenger age. And this is what you're seeing. Basically, I have for all the females in first class, I have summed the passenger age data, right? So this is what we see here. All right. A fundamental operation is to convert to long format. So the data here, I have taken the ID and I have unfolded it in this way. So whoever was the person with ID 1, you can see that the variable passenger survival, they has a value survived, and so forth, right? So I use this kind of transformations a lot, not just for say recommenders, which I was showing earlier, but for any kind of machine learning. This here is, I guess I'm showing off here. So this here is actually generating code from a natural language specification to generates Raku code for filtering, right? And you can see how, and this again illustrating the advantage of the approach I'm taking to data wrangling. You can easily translate this into some built-in function, right, for filtering of the data and so forth. Type deduction. Very important. So you can see I'm not going to expand too much on this, but I have developed or implemented type deduction system. I have appropriated the solution which was in Mathematica for datasets, and the datasets in Raku, they as a strategy, they follow the datasets in Mathematica. So you can see, let's say for this Titanic data, it's a vector of 1309 records, and we have this association of string against string. This is because the passenger age was not converted into a number, right? It's just read it from a file or whatever. But here, if we convert passenger age into a numeric, to be numeric entities, right? We can apply this deduce type function again, and we can see what we have a structure, right? So the structure is basically this keys, it, passenger age, passenger class, and so forth, being translated into string, int, string, and so forth. And you can see passenger age corresponds to int. And yeah, I mean, we see what we have, how many elements we have in the dataset. All right, so I would like to kind of mention, compare the two approaches. As I mentioned, mine is minimalistic. Hopefully Steve Rowe is not too annoyed by my comparison here. He can also probably fix it, like in his talk. So I would say Dan's approach is deceptively simplistic. Mine is dataset based, Dan's approach is data frame based. I mentioned the minimalistic or minimal viable product motivation. I just want to have some data wrangling functionalities in order to do my machine learning implementations and studies. I think done is much more performance oriented, right? So it's like, this is why I was showing these big trucks with, you know, kind of big data, big pipelines. I would say the orthogonality goes even further. I take more functional programming perspective. Dan uses more like methods and object-oriented type of perspective. My approach is very heavily inspired by Mathematica. Dan is inspired by Python, and Python pandas, for example, which is being used as a, you know, as an example to follow, right? As an implementation to follow. It's very much inspired by R. And another thing is what. There's some other things here, like in my approach, like I use Mathematica notebooks, Steve is using Jupyter notebooks, Steve wants to connect Raku and Rust. I'm more interested in, say, connecting Raku and Mathematica with Swift and so forth. All right, so we go to this tries with frequencies, which is an unsupervised type of algorithm. And so I'm going to kind of bring this mind map again. So we're in the unsupervised learning, and I'm going to talk about this tries with frequencies, right? Okay. And so we have this list of words, ba, 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 bark, bark, ka, and so forth, right? And I can generate this, what happened here? Yeah, I can generate this corresponding prefix tree. So I can see I have 11 words, and 5 of them start with B, and then 5 of them continue with A, and so forth, right? Now, they're called tries or prefix trees because I can, of course, shrink this, right? And so, if I shrink it, I see that from this, there are 5 words which start with Ba, and 2 of those 5 finish with K. And similarly, 6 words start with C, 4 of them continue with A, and 2 of them continue with Aster, right? So, okay. Now I have some representation. I can represent these prefix trees with as hash maps, and this is what we see here. And so, let me see. I'm going to use the command line here again to generate the UML specification. So this is going to show, I would say it's fairly comprehensive list of functionalities on this. What happened? All right, yeah. So yeah, okay, something is happening with my preview, but anyway, right. So there are quite a lot of functionalities in this prefix tree, right? And I'm using different traversal methods for this. I mean, it's not, we're going to see some examples, you know, how is this being utilized and used. All right, so I was showing that, yeah, I mean, I'm using the original Titanic data here, right? And so here I'm going to just use the passenger sex, passenger class, passenger survival, and I'm going to make a prefix tree. And so, so I was saying earlier with the cross tabulation, this is what the corresponding data is. I mean, I can see fairly quickly here by this, but say females and you know, females who are first class, you know, how many of them are, how many females, how many of them are first class, how many of them are second class and third class, and so forth, right? So now this mosaic plot, it's based on prefix trees. It's not necessary to use prefix trees to make the mosaic plot, but it's one way to do it. And you can see, say, for the different passenger sex, like say female, male, right? I can see in this big block here, this big square, almost square rectangle, that 64% of the passengers were male, and of those 37%, 30% total were male and third class, and from the male passengers 58 were, you know, percent were in the third class, and so forth. And then so this particular thing you can see on the right, it's corresponds to die, to the passenger survival. So I can see that, say, males who were in the third class, there was 85% probability that they have died, right? So, all right. So yeah, this is so prefix trees can be used for to study the data in this way. I can also convert the nodes into from frequencies like integers, right? I can convert them to probabilities, and so this is going to produce some kind of conditional probabilities. And if I have this, like say for example here, this tells me that okay, there's like 35% probability to be female, right? And then 30% to be probability to be in first class. And given that female and first class happened, we can see that 97% survivability is here. All right, and yeah, you can same for the others. Again, this is like some sort of this mosaic plot what I was showing in this diagram here with the prefix tree. They kind of show that prefix trees with frequencies can be seen as some sort of naive Bayesian classifiers or some generalization of naive Bayesian classifiers, and this is what is happening next, right? So I can classify, given male and first, I can classify to a label like died or survived, right? And obviously, you know, I can generalize this signature for classify to use different to be on list of records. And I'm going to get this type of comprehensive labels, right? Probabilities. What happened? You know, what is a probability? Not just get the label itself, but get the label plus the probability for that label. Okay, so in this mind map here shows the machine learning general machine learning classification workflow. It's a mind map for the machine learning classification workflows. We have some data which is being given to us by certain judges. Judges can be reality, but it can be also, say, the Netflix prize committee. So Netflix prize, if you haven't heard, like 10-12 years ago they had a prize, I think 15 years ago actually, so they had a competition who is going to improve the scores of Netflix. And so if you improve the scores more than 10%, you know, they're going to start considering giving awards, and then whoever has improved it the most is going to get the award. It was $1 million or some $1 million. So you have the training set, they have a testing set, but they are not sharing this with you. They're going to judge your classifiers based on this testing set, and they can give you the actual records, but they're not going to give you the results, right? So so this is one of the things. So we get the training data set, and then we, with the training data set of the judges, we split into a training and testing set. We're trying to find or make a classifier. We can do this multiple times. We can apply different methods, different splittings, different type of data massaging, whatever, right? The data wrangling and so forth. We can evaluate it with confusion matrices or receiver operating characteristics. I'm going to show what these are. And after we have found out a good enough classifier, we have given up to make a good classifier, we train with whatever method we came up with, we train it over the whole training set from the judges, and we give it to the judges. The judges, they don't want us to kind of make too many submissions too frequently, because in this way we can probably figure out, you know, what exactly is the testing set. So, you know, there's some kind of restrictions how often, and you can, you know, submit your results for the testing set. Okay, so the receiver operating characteristics, and again, going to this example here. So, I mean, here I might say that the probability for male and first to die, being 60%, died has been chosen. But why I'm choosing died? Because this is larger than 0.5. Where this 0.5 threshold comes from? And, you know, it seems natural to use 0.5, but it might happen that I might have better performance results if I want to predict survivability, if my threshold for died is lower, or if my threshold for died is higher, and the other way around for survived, right? So this is what receiver operating characteristics are. So we have, let me actually see. So there's like this paradigm of the receiver operating characteristics, which was developed in the Second World War. You have a radar, like some kind of radio location type of device, and you're like, say, directing it toward airplanes that come to the back of your army, right? So how much you want to shoot your own plane? Like your radar might have some kind of way to recognize, but how much do you want to shoot your own plane? How much do you want to let an enemy plane go to the back of your army? So anyway, there's a quite a lot of functions within this nomenclature of which is prepared by the receiver operating characteristic. The ideal classifier is going to be this kind of angle here, right? So this is here shows the trade-off between true positive rate and false positive rate. In reality, we very rarely have this kind of ideal classifier. Most of the classifiers are somewhat curved, and you can see we can have different measures like area under the curve, for example. Mostly, I would say we're interested into the true positive rate and false positive rate. All of the functions, they can be computed with based on these functions: the true positive, true negative, false negative, and this is what you see here, right, in this slide. So for this tri-based classifiers, I have evaluated the receiver operating characteristics for different thresholds, like 0.025, I think, or whatever, and I have calculated this for values, and then I have calculated the receiver operating functions, false positive rate and true positive rate. So this is from this package, ROC functions. Yeah, here is the textual plot, but it's kind of zoomed too much. So this is the corresponding mathematical plot, and you can see here this is 0.3, right? So you can see here, but say with the threshold 0.3, this is for survival. I see 78% recognition, true positive rate, at the expense of 20% false positive rate. All right, so as I said, quite a lot of functions being put or used in this receiver operating characteristics framework. So it's a very good idea to have some kind of supporting functionalities like this in the package, right? Like, say, ROC functions properties and the function interpretation, being able to retrieve the actual functional objects by the specifications, which are, say, more easily understood or more easily known. This is something I'm not planning to just do for the receiver operating characteristics. I want to do this across all machine learning packages to be able to help and retrieve as much useful information as possible. So clustering, it's unsupervised learning type of activity, and so we have it's fundamental. It's one of the probably first things you do machine learning wise with data. Distance functions, which are used in heavily, of course, in clustering. These distance functions, I strongly suspect I need to make a separate package, factor them out of the clustering. But yeah, we can see I have plans to implement at least 2 or 3 more clustering methods. We have quite a lot of clustering methods which have different types of utility in different kind of situations. So here I'm generating a bunch of points, like 1,000 or something, and then I'm generating a plot for them. You can see the corresponding mathematical plot for this textual plot, and then I can cluster them using the find clusters function, which is using k-means, and the distance function Euclidean, and then I can plot them, right? And so you can see, like here in this text plot from Raku, in Raku, right, made in Raku, the centers of the mean points of the clusters were shown with these very saturated black dots, and the actual clusters, these 5 clusters, they have been pointed out by the symbols here. Interesting point here is that how come I have 5 clusters? Well, I'm observing the data after I plotted it, so I decided to put 5 clusters, right? But in general, it might be interesting to do something like this, right? To kind of automatically find how many clusters we have within the data. This is well in my to-do list to do next. All right, fairly straightforward after we have it, right? So it's a good point to compare the different distance functions, and so here I'm showing using this data with say using Euclidean function and using cosine function. Now Euclidean standard, and I have said that I want 3 clusters here. That's why we have, you know, these 3 clusters have been found. There's some stopping criteria, you know, when it's ultimately k-means is some sort of optimizational method, and there's some kind of stopping criteria. That's why probably the clusters are not perfect. There's some points, you know, from one cluster to another, and I have said that I want 3 clusters. That's why, you know, these clusters are very close to each other. Now, if I use cosine distance, cosine is actually directional distance. It's not proximity. It's not proximity like Euclidean. So in a sense, we're looking into the direction from 0, right? From 0, and that's why we see the clusters, they're more like this kind of angular type of distribution. One of the big things about this is what, let me see, can I show this easily? This needs to be extensively documented. I plan to use this kind of stencil, which is also used by Wolfram function repository, in which we say the scope of the algorithms, what are the control parameters, and you know, extensive discussion of the control parameters and the effect on the results, example applications, and hopefully I have shown, yeah, possible issues. Of course, some neat examples. Neat examples here, I have rasterized a certain formula, x squared plus y squared equals 1, and I'm applying clustering on top of that formula and see, can I actually detect the different symbols from this. All right, so so here another unsupervised, actually it's more like statistical algorithm and more of a data wrangling, data analysis type of algorithm. So it's outlier detection. So I have generated here a bunch of points. You can see I have used normal distribution with mean 12 and standard deviation 6. Actually, this should be... All right, yeah, obviously it was wrong. So I have produced these 50 points, right? And I'm using data generators, a package called data generators. Here we're going to invoke an outlier identifier which identifies the points. If I don't have values, this is going to give me positions, right? But I can also use the adverb values, and then we're going to get the actual numbers, right? And I can also sort the data, and after I have sorted, to kind of show the outliers. And you can see I'm showing both the bottom outlier and the top outlier. This is a very powerful actually technique to have a selection, a nice selection of one-dimensional outlier identifiers. You can make some fairly complicated multidimensional data outlier identifiers using one-dimensional ones, and based on these distance functions, for example, and some other things. All right, so related semantic analysis is not something we can do in Raku right now. Well, we can do it for some very small type of examples using the dense matrices which are implemented in some package, like I think it's called math matrix. Now I'm going to actually show this. This is actually probably quite an interesting example. So this here, I have this notebook shows how I have taken Raku guide texts from different languages, and I have combined English, Spanish, and Russian, and I have combined them in such a way that these are in this pot format, right? And I have separated the text data from these guides, Raku guides, into different sections or chapters. You can see that from Bulgarian one I get 65, but from the English, Spanish, and Russian I get 71. So again, I guess the Bulgarian one was not updated recently. these three types of documents, I take each of these 71 from each of these languages and make one document. So basically I have 71 documents now combined, in which one of these 71, it has all three languages, English, Spanish and Russian. You can see here, this is a cell which I'm using Raku underneath to generate. This is converting the notebook into DSL mode, and I'm using this DSL cell which uses Raku to convert natural language specification into latent semantic analysis pipeline. And so we have, like, say 71 documents, 5,698 terms and so forth, right? Here I'm extracting the topics. You can see the topics. I'm not sure, you can see what, say, some of this, like say chart, bar, obviously bar chart, right? Kind of connect to each other, but the orthogonal version of view on the topics is the statistical thesaurus. Let me zoom this a little bit more. So in the statistical thesaurus, you can see here what, say, words like, say, expression, right, in English. You can see both the English and the Spanish word corresponding to expression. This here, it's the Russian words, if you don't know Russian, to expression. Similarly, for object, we have object, objeto, right? Attributes, it's like related and so forth, right? So this this technique of translating, in a sense, we can say the statistical thesaurus translates one language to another, right? And this technique for translating natural languages was used by Google Translate, saying 20 years ago, right? So they used say 50,000 pages per document, so 50 languages with 50,000 pages each from UNESCO documents. I think this was the original project. All right, so okay, we cannot do this in Raku, but this package, Streams Blending Recommender, ML Streams Blending Recommender, this Raku package knows how to use this kind of artifacts. I was using actually the outcomes of the latent semantic analysis, topic extraction, statistical thesauruses. I'm using them, for example, when I was showing some of the stuff in Python and also in the Swift examples, right, with the mobile devices. This here was, we already went through that. Association rule learning, very very important technique, right? So again, this is unsupervised learning. So this here takes the so-called adult data set, in which we have this data. We have ages, education, marital status and so forth. The idea is, from this data here, can we guess who has income less than 50k and who has income more than 50k? So this data is from, I think, late 90s, or so that's why it's, say, only 50k, right? But the question is, what are the frequent combinations of data elements here, of actual values, which say strongly associate with the income or anything else, right? But what are the frequent sets? And so one way to do that, and here I have the summary within Raku doesn't, because the data is too large, doesn't look that well, but that good, but I have summarized it here within Mathematica using this Raku input execute command, right? And so I'm transforming the data into baskets. I'm going to, in order to make more kind of quick to compute interesting example, I'm only taking education, marital status, number of education, right? Education num is the number of education years, occupation and income, right? And so here these baskets, how they look. I am using the name baskets because the alternative name of association rule learning is market basket analysis. And yeah, I mean, we have this kind of basket. So here we can find frequent sets. I'm saying find the frequent sets within baskets which have support 5%. So at least whatever kind of frequent sets of combination of things, like say in this particular case, 50k HS high school graduation, never married, right? This has been 9.5%, so almost 10% kind of representation in the data, right? So this is what this frequent sets is. So This is a frequency set because, well, it is above the threshold of 5%. And the question is how to effectively and quickly enough find these frequency sets. And here I have isolated the frequency sets which produce more than 50K, right? And so we can see, say, if you have more than 13 years of education, if you have bachelor's degree, 6% of the time, 7 almost we get higher than 50K, married with civic or civil spouse, 5% and so forth. So the question now, it's interesting, in what direction are the rules? Like, imagine you're looking at the shopping carts in some big store, right? Like say Walmart in America, I don't know, Aldi in Europe, and say 10,000 shopping carts every day, right? And so you see what people who buy, say, jelly, peanut butter, and bread very often. People buy bread, peanut butter, and jelly very often. Now, 80% of the time, if people buy jelly and peanut butter, they buy also bread. But the other way around, it's not true. If they buy bread, they don't necessarily buy peanut butter or jelly or both. So this kind of direction is not just to find the association rules, not just to find the frequency sets, but to find the association rules. And so here I have identified the rules. There are some different kind of metrics which I used. Say confidence, it's confidence and support and so forth. I actually did this. Let me see. Okay, I guess I just restarted the whole thing, and it's a long computation, so I'm not going to do it now. But yeah, basically you can see here, I have, maybe I'll zoom out here to kind of show how this looks in Raku, right? So in this computation, I have found the antecedent, the consequent, and I have found different metrics related to that. They're kind of shuffled because since I'm using arrays of hashes, Raku by default shuffles the hashes, So if I don't take care of it, right, we get this kind of shuffled tables. But anyway, this is another thing which is being used by associative rule learning, is to actually find the rules, the direction in which things are happening. And you can see here in this particular, let me kind of go back to my zooming here. Actually, I'm going to go to 200 to kind of show this table here. So you can see what, say, if the married, civil spouse, and professional specialty with confidence 70%, we get more than 50K as a consequence. And the support is, say, we have 747 of those instances which this has been observed, and we have support of 4.5%, and we have some other metrics like, say, lift and leverage and conviction and so forth, right? So yeah, okay, so I'm going to just go to my 150 zooming and then go well, some people apparently feel very strongly about command line interfaces. So yes, check the command line interface mate. It is very important to endow all these machine learning algorithms with command line interfaces. So and I'm going to basically repeat what I was showing earlier. There should be some kind of more or less universal design. I do think this is a good design with using functions as a front end and object-oriented programming to have some comprehensive methods behind them. The facilitation of the machine learning investigations, results, experiments with notebooks and textual plots and tables, very important, especially if we talk from the so-called reproducible research perspective. I would say that's important. Fast data type deduction, we kind of saw examples of this. I also commented of my model storage and deployment facilitation. Yeah, I wish, I'll be very interested to kind of further research and investigate Raku's applicability and speed ups here. Unit testing and correctness together with proper documentation, extremely important. All right, so this is in response of what the previous speaker was saying. I was asking about did he become better programmer for or faster learning other languages after learning Raku? I would say I was very quickly became the best Python programmer I know after learning Raku for a few years. And I mean, I'm not sure should I be showing this here, but yeah, okay, well, there's this it's a very interesting project to make a code of conduct compliance classifier, and what kind of data to take from where, right, in order to do to train the classifier and verify it, right? I mean, I can take, say, data from Discord and try to use some profanity classifiers or outlier detection or whatever it is, to kind of get to make this kind of classifier. Well, this was it, and yeah, thank you for your attention.